All right, here we go. Let's do some logarithmic equations. Shh, quiet down. Here we go. So log graphs. Let's investigate log graphs. Now log graphs are inverses of your exponential graphs. So if you know your exponential, you should be able to predict what your logarithmic graphs look like. So here we go. I'm going to draw your exponential graph. And then you tell me what are the features of a log graph. Okay, so here we go. I'm going to do it in blue. This is my exponential graph. It has 0, 1, asymptote along y equals 0. Now because it's an inverse function, logarithmic is inverse of that, you should be able to predict what that graph should look like. So what would logarithmic function be? If this is y equals to e to the x, then what is y equals to log base e of x look like? Give me the properties for that one. Again, you should only have 2. Name me one. What's one property? One property. Yes, Jack.
X-intercept.
X-intercept, which is what?
1, 2.
1, 0. Fantastic. The x-intercept is the inverse. So if it's 0, 1, the inverse is switching the x and y's. It becomes 1, 0. So you got 1, 0. Yes, you have an x-intercept at 1, 0. What else do you have, Sharon? X equals 0. What is that? Asymptote. You got a vertical asymptote. So unlike your horizontal asymptote, you now have a switch, which is now the vertical asymptote. Instead of y equals 0, it is now x equals 0. And if you draw that graph now symmetrically, whoops, what is that? Oh my God. All right, there we go. Let's do it again. There we go. If you tilt your head, you can sort of picture it's this symmetrical look. Yeah, it's a reflection in y equals x. So this is what my log graph looks like. That's your properties. You've got the asymptote has to be at x equals 0. You know that it crosses through the x-intercept at 1, 0. So now you apply your transformations. Whatever you apply the transformations to, it just changes the shape. Okay, so let's revise. What does the easiest one? K. What does K do again? Can I please have, let's snaz. It doesn't shift the asymptote in this case. It does shift the exponential graph, but it doesn't shift the logarithmic graph. Why is that? What does K do to the graph? It translates up and down. Now, if you think about it, the asymptote is always at x equals 0. So even if you move it up and down, it's still at x equals 0. Yeah, so unless you move it left and right, you move it left and right, that's when you move the vertical asymptote. Okay? So in this case, yes, K moves it up or down. So what does it change? If K moves up or down, what does it change? Out of the two properties, it doesn't change the asymptote, but it must change. It's got the y-intercept. The y-coordinate. Good. Now if you think about it, if I shifted this graph up, would the x-intercept be less than 1 or is it greater than 1? Logically. Less than 1. Yeah, because it'll be, if you shift this up, that means all these coordinates are likely to hit this point, and that has to be less than 1. If you shift it down, then it's likely the x-intercept will be greater than 1. Okay? So this is responsible for up and down. K is responsible for up and down. What's B responsible for again? What's B do? So if I had 2 log e of x, what does the 2 do? Dilation from? Which one is it? X-axis. Are you sure? How do you know? Yeah, it changes the y because we know if y equals to log e of x, if I wrote y equals to 2 times log e of x, technically log e of x is the same thing as y because that's what you said. You said y equals log e of x. 2 times the y means you're affecting the y values. Now remember, when we're stretching, if we're stretching the y values, dilation of factor 2 is moving away from the x-axis. This is moving away from the y-axis. Okay, so this is the y-axis, it's the x-axis. So if you're doing this stretch, it's moving away from the x-axis. Okay, so we know that B tells me it's a dilation of factor whatever it is, so factor 2, or factor B, sorry. Factor B, dilation from the x-axis. Yeah, I don't know what that is. It just keeps doing that. There we go. From the x-axis. What does C do then? What does C do? Yes, good. It'll be a dilation of factor C from the y-axis. Okay, so we've got C is a dilation of factor, but I just said C. It is not factor of C, it is the factor of 1 on C. So that's the only thing you got to be careful of. Anything you do with the x's is what it does there. So we've got C, it's a dilation factor 1 on C from the y-axis. What does the D do? Technically, it's not even the D. It's something else. How do you move it left or right? What would be responsible for left and right? Yes, Kate.
You make everything in the brackets equal 0, for example.
Fantastic. Very good. It's this entire bracket. C times x minus d will affect whether you move left or right. So that's what we're changing. That's what we're replacing with x. If you remember from chapter 3, this is your new x. That's your original x. So if you move everything, it's technically d over c units. Okay, so d over c units there. So just to spell it out so you can see what I just did, I'm just saying, this is your original x. Oh my god. That's your original x there. You're now replacing that with cx minus d. So really you're saying the new x is equivalent to the old x multiplied to c minus d. So if you rearrange that, that will tell me now x dash plus d over c is equal to x. Okay, and you can now see if you split that fraction up, that's what you're doing. And you can see that's why it's moving by an amount, and it's a dilation factor of 1 on c. Okay, dilation factor of 1 on c plus d on c. That's why it's not just d. Okay, and the reflections, where do reflections come in? So I had dilations there. I've got translations. Where's my reflections? How do you know which one's reflections, and Sarah? B and C again. See, B and C, reflection and dilation are the same things. They're timesing the function. The only difference is it's timesing by a -1. So if you change B to a negative B, what kind of reflection is that? What do we call that? Reflection in the x-axis, because you're affecting the y value. So just picture a coordinate, and if you flip the y-axis along the x-axis, you can see it's flipping the y coordinates. Okay, so if you flip the y coordinates in the x-axis, if you're flipping the x coordinates, it's on the y-axis. Okay, so this would be reflect in y-axis, whereas this is reflect in x-axis. Pretty easy. Okay, that's exercise 5E, and that's what I'm saying. You find that everything is interlinked. If you understand chapter 3, it naturally flows with this one. The only thing you had to learn was the properties. Once you know the properties, you know the shape. It's very easy to do. Yeah? So let's do some examples. I'm just going to move on to the next slide so you can see. Where is it? Here we go. Let's do... Where's my questions? Here we go. This is from your textbook. I want you to each tell me, I'm going to name each, how many do we have there? We've got 1, 2, 3, 4, 5, 6, so there's 12 questions there. Let's go with A. Tell me the transformations for A. Can I please have Rachel? For 3A, just looking at it, you got y equals log base 2 of 2x. What kind of transformation do I have? Name me one. 1/2, because you're dealing with the x. So from the y-axis. Fantastic. So that just makes it compressed towards the y-axis. Okay, so we know it's thinner. So that's A. What about C? Let's go with C. I'll go to B next. C. Give me, what is this one, Phoebe? What kind of transformation do I have for C? Good, reflection in the x-axis. I'm affecting my y values. Fantastic. So if I were to quickly draw each one, this just makes it thinner, so it may look like that. Whereas this one, reflection in the x-axis, so it looks like this. Okay. Next one, E, Zan. Name me one transformation that I have here.
We have a reflection in the y-axis.
Fantastic. And what's the other transformation, Chi?
Translation of 5 units in the negative direction.
Not negative direction.
Positive direction.
Positive direction. So if you rearrange that, I normally say just let that equal to 0 and solve for x. Okay, that's just normally how I do it in my head, because that 0 is really your x dash. You don't need to know the x dash. Yeah, you just need, I mean the x. So technically if you solve for x, that just equal, oh my god, equals to 5, and that tells me positive 5 units to the right.
Is the base of the log affect the graph?
Yes, it does. Joe was going to ask that last, but now that you're asking it, what is the difference between log base 2 of x, log base 3 of x, and log base, let's say, 9 of x? Can someone think? Think before you speak. Because if you know exponentials, then you know logarithmic. They're all the same things. So think about it. If I change that to exponentials, which I'll do on the side for you, 2 to the x, 3 to the x, oh, whoops, 3 to the x, and 9 to the x. So if you think of the graphs, how does it affect the log graphs? Try to picture it, and then put up your hand if you have a particular answer. Yeah, it does get thinner and wider, just like exponential. So I'll draw the exponential, and then I'll get you to see how it's similar with the log. So here we go, exponential. I'm going to do the blues. Blue for the first one, 2 to the power of x. So let's just say this looks like 2 to the power of x. It crosses through 0, 1. So this is 2 to the x. Now when we do 3 to the x, what do you expect? What do we know? Yes, it shoots up from the positive side, but it swishes down in the negative side because it gets smaller quicker and it gets larger quicker as well. So I'll do in green 3 to the x. So there we go. This is 3 to the x. It looks like that. This is 3 to the x. Then what about 9 to the x then? Even more. Okay, so I'll do it in purple now. So you can see that it will go even further up and further down. And this is 9 to the x. So now logically, if you were to sketch your log graph now, it is reflected in the y equals x, where'd it go? Y equals x line. So what you can expect now, it's exactly the same thing. They all cross through 1, 0. So I'll do the blue. So this is 1, 0. And I draw it, and this is your a log base 2 of x. Okay, log base 2 of x. Now what can you expect for the green graph? What would that look like now? What do you expect? Okay. So if you try to draw that same reflection, if you try to do the same reflection there, what you should expect. So the green should look like this. True, it gets thinner in the positive direction for the y values, but then in the negative direction for the y values, it should be smaller. See what I'm doing there? It gets closer to the asymptote. Yeah, and then you can follow the same thing. So if you look at it symmetrically, that's what it does. Okay, so the base does change it, but that's the logic that you need to understand. It just changes the starting point. Yeah? But I don't know what the name is to that. They don't call it dilation or anything. It's just a change of base. Okay? But there you go. Let's go to G now. Sorry, we're up to G. Let's do G. What's the transformations for G? Name me one of them. Can I please have, who have I chosen? Let's go with Luke. Luke, G, 3G. Name me one transformation that you see.
Reflection in the y-axis. No, x-axis.
X-axis, fantastic, because you're affecting your y value, so reflection in the x-axis. What else do you see? Can I please have Aiden? What do you see in G? Dilation of factor... Not factor 3. You 1 on 3. Fantastic. So dilation of factor 1 on 3, because anything you do with the x's are reversed. So it's 1 over 3 from the y-axis, which is correct. Okay, and then finally, number 2, what does the 2 do? Can I please have Jack? Good. Factor 2. Okay, factor 2 from the x-axis. So if you were to draw this now, you know that instead of it's reflecting the x-axis, so it has to look something like, whoops, not like that, like this. Okay, but then it's also dilated by a factor of a third from the y, so what that means is it's compressed towards the y. Okay, so it makes it thinner on the bottom, so it will now be compressed. So I'll do it like that, that's compressed. And then not only that, it's dilated by a factor of 2 from the x-axis, so it's even more compressed. So you can draw it, you can draw it like that. Okay, it gets even wider out, it's thinner. Okay, but that's the expectation. How does that feel? Is that all right? Okay, so that's exercise 5E, and that's all I need you to understand. But you see, if you can practice doing your chapter 3 revision for your own SAT, it really lends itself to this one very easily, because every chapter is the same. When you get to circular functions, it's going to be the same thing. Your period and your amplitudes are based on the same transformations. So you get the basic graph, you get the properties, they all do the same things. Okay, so revise for your SAT. Chapter 3 was the big one. It was 3a to h because it lends itself in every function. Okay, so learn your transformations, learn the sketch, learn to read the domain and range. That's how they all do it. Okay, but that's it. That's exercise 5e. We'll go on to, once we do the revision Friday, we'll get back into chapter 5 and try to tie it all up together again. Okay. But Olivia, there you've got. What time did we finish? 5:45. So you've got about 8-9 minutes before the end of class. So you can do your revision, or bout reference, or ask me questions or tips. But tomorrow I'm doing that booklet. That's what I want to do. Okay, bring your CAS as well. Bring your CAS as well.
Rate of change of the gradient. I know, you rate of change, you need to figure out whether a point of change is a big or an actual line. My point is here, I did it with 2 and I got that. I did it with -3 and I got the same answer. As like the exact same. Anything special coming from that?
And it had a definition, but yes, the turning points you don't include. Yeah. So they'll always have it as open brackets. Though I disagree with it, that's how it is. It's just how it's written. So your textbooks have done it all right. That's what I confirmed after it, is that your textbooks are all correct, based on what VCOB wants. Based on what I understand and how I read the definitions, then I still think I'm right. It's just how VCA's decided on the definition. It's more of a definition, really. But I remember putting it somewhere in here. Was it in chapter 1? Function. Yeah, there we go. Strictly increasing, decreasing. Oh, it's not loading. I just opened this one. Come on. Open. Alright, here we go. In the VCA description, let's find an example.
What's that? How do you do it? Question.
What is it? The function is said to be strictly increasing over an interval from A to B, as long as f of A for A to B, thus is not strictly increasing. Well, that's obvious. Anywhere that's decreasing. Huh. Let me find it again. Strictly increasing 0 degree is the vertical tangent. So here your turning point is 0, but overall
Oh, I am high. I'm high.
Yeah, so in that case there, so the gradient for this x cubic graph, it's undefined at 0, but it would say that it's strictly increasing throughout. So it says here it's strictly increasing with 0 gradient at the origin. And it doesn't say what the interval is. Because it's talking about the y values. The y as long as it's greater than, then it doesn't matter. It's strictly increasing overall. Let me find another one that I remembered. I think it was it this one? This graph. So in this one here, it is strictly decreasing over the interval 0 to pi. Wait, figure 7, sorry. 0 to pi. That's weird. That's increasing. I mean, including the interval. Oh, that is including it. Maybe your textbook's all wrong then. This is from Vika, so you do include the turning points. Let me find an increasing one. So this is decreasing. You include 0 and pi. What about increasing? Strictly increasing over the interval will be strictly decreasing on the same interval. For example, something is strictly increasing. Yeah. According to this example here, you do include the maximum minimum points. So you're right. With that one, what kind of graph did you have for that one? And it was 0 to infinity, wasn't it? I mean, the minimum point to infinity. Is that right? And minimum was at x equals half?
Shit. Oh, shit. Oh, no.
Let's find one where it has an endpoint. What about this one? Yep. Include it. Ignore the textbook. According to what Vika said here, you include the turning points there. You do. And if it's increasing, so if it doesn't say strictly, then you don't include it. You don't include the derivative points. It's not including them. Yeah. So if it's strictly increasing, you do. You do. Yeah. Yeah. See, that's always strange because if you read the definition, what they've written there, I really think my interpretation was correct. I don't see how I'm wrong. But based on what they're shown as an example, you include it. Include the turning points for strictly, and you don't include it if it's not strictly. Yeah. Yep. Strictly means that you include the turning points, and not strictly you don't. Ooh. Chapter 9. Did I not put... It's not on Schoology? Chapter 9. I thought I had every test. Chapter 9. What was chapter 9? Let me write that in my diary, because the internet's a bit slow. I'll write that in my diary. Tuesday, Wednesday. Chapter 9. Year 12 solutions. Is that from the test I gave in class, the assignment? Not like a take-home test? Is that the one you're talking about? That I gave to you and then you said you would return it to me to mark? Is that the one? Yeah, I'm pretty sure it should be there. Let me just double check that one. Chapter 9, differentiation. Chapter 9 test. Yep, it's right there. Yeah, there's a chapter 9 test in class and test in class solution. Let me open it up. All right, thank you. Make sure Friday, I want your bound references in that plastic pocket to return back to me. Other than that, tomorrow's your revision. Bring that booklet in.
That's point.
No!
That's exact point.
Oh!
Yep.
Oh, that'll make this so much easier. So I know how to do Untitled question one.
Wait a second.
I wish I remember using quick method.
Is it this one? Banu? Banu?
Wait a second, this cat is lying to me. What the hell? What the hell? It's lying to me, Jack.
Is that the one? Alright, cool.
The cat's lying to me.
Hey, we got baited. I don't know how to do it.
Cat's lying, Jack. That's not the point
Are
of
you going to be
the
any risk after?
No, I'm chasing after kids, but I was going to help Antero before I run away. You figured it. Oh, hey, cool. Alright, well, time to chase kids then.
Get me down to like 30. That's right.
Oh, that was